Welcome students, this is the lesson number 13 under which I will like to discuss on GPS point positioning. So in this class actually I will like to show you the mathematical deduction of the GPS data, how we arrived at the position of a point. So now this lesson as will be consisting of introduction and GPS positioning, and I will like to take up the pseudo range observable of a point, and that from that I will deduct the mathematical relations how it conclude to the GPS point position. And the same way actually we can make use of single code, multi code or single frequency GPS phase observables or multi frequency phase observables, but the idea of arriving at GPS positioning is same. So I have taken up as a CA code pseudo range observable for deriving the position of point. Now as we know, already we have discussed that original pseudo range from satellite I to receiver R at an instant of time t. In the last class we have discussed that the pseudo range will be preprocessed, and after preprocessing we will get some pseudo range value. Suppose this is dash, pseudo range dashed, that means now we have removed some of the errors and this is the new value of the pseudo range observable, and it will consist of the geometric range plus error due to receiver clock and other errors. So this is a, suppose I have written a defined E, so that you understand that the errors that were available like your satellite clock error, ionospheric error, tropospheric error, then many other errors that has been removed, many of the error has been removed or minimized. Ultimately some error is there which is, I can say, as residual error. So now this is the pseudo range which we have, pseudo range value, and this pseudo range value consists of these. Now this is the residual error and this is the thing. Now from here we have to find out the position of receiver, position of the receiver from which we have taken these observable. So let us assume that the position of the receiver be XR, YR and ZR. So to get the GPS position we need to find out these 4 parameters. So these 4 parameters are the unknown, which has to be determined by using this value. Now as I have already told in GPS point positioning that and also you know that to determine 4 unknown we will be in need to have at least 4 satellites, that means signals from at least 4 satellites, and usually we take data from more than 4 satellites. So we go for now when the number of observations are more than the number of unknown, number of observations are more than number of unknown, then we have to apply some statistical, we may apply many other methods. Generally we use least square analysis, least square analysis method. So we have to go for to determine the position of the receiver and the clock, receiver clock error, these 4 unknowns, we will make use of least square analysis. Now least square analysis of GPS data, of GPS observables which are preprocessed. Preprocessed means we have removed and many of the errors, and also we have minimized the amount of error, and the observables now will have only some residual errors. So and with these assumptions we will start. Now suppose this is the unknowns, and as you know that the signals are coming. So suppose this is the terrain and this is the point P where whose position x r, y r, z r we need to determine. So at this position what we will do, we will set up a GPS receiver, and that receiver will receive signal from GPS satellites. So let us take at least 4 satellites. So So 1, 2, P, N. So now as we know, as I have already told, it was told in this class, that each of these satellite will have some coordinates or location, and these coordinates or location of the receiver will be available from navigational data, and suppose x to the power p, y to p subscript, z p subscript, these are the superscripts, shows the coordinate of the particular satellite, x to the x n, y n, z n. This is these are the location of the satellites which will be available from GPS data. Now if we know this thing, and if we know this thing, then we will be able to get, suppose this is 1 and receiver R. So you will have the equation x1 minus xr y superscript 1 yr z zr. So all of you know this is the distance equation. Now but we do not know what is this value. So we will not be able to know what is this value. So there lies the problem. Now how we resolve it? As I told you, we will go for least square analysis to find out these values, but least square analysis require linear relation to resolve, but this is a non-linear equation. You can see this is to the power 1, this is to the power half. So this non-linear relation first has to be linearized. So how to do it? Now as per our assumption, our pseudo range this is equal to this is a function of x r, y r, z r, del t r plus this r t. Now to linearize it, actually we have to assume some value for the GPS receiver. Now suppose x0, y0 and z0 assume value of the unknown station. Now then xr minus x0 will be del x, del y will be yr minus y0 difference, I should say difference, and del z is the z0 zr z0. Now this del x, del y and del z are the errors between the assumption and the actual value. So now if we assume instead of this, if we assume this, then we can write this function as f of x0 plus del x, y0 plus del y, z0 plus del z and del t 0 plus del t. So this is the thing we can write. Now in writing this, now these are known, but these are unknown, del x, del y, del z, del t. Now the problem is not to determine x or y r, but to determine del x, del y. So this is the thing. Whenever we go for GPS observation, we generally need to give the approximate value of the location. That means we have to give the value of x0, y0, z0 and del t0, and from there they compute iteratively the del x, del y, del z, and then that has been from there we do determine this position. Now still now the relation of that modified pseudo range is can this, and now we can make use of Taylor series. All of you know that this will be x0, y0, z0, t0, del t0. That means in this relation we will, instead of xr, we will, if we put these values, then we will be able to get approximate geometric range which is known, plus now from Taylor series, taking the first partial derivative, we can write del x into dfi by del x plus del y dfi by del y plus del z del f I plus del z, and then this error plus e to the power this. So in this can be computed and known, this is known and this is known, and this is the thing which is unknown, where del x del y this is unknown. Now and this, so we can write that P r dash I r t is equal to f of x r y r z r del t r plus e I r t is equal to, now this x 0 y 0 z 0 del t 0 plus x del x means x r minus x 0. Now dfi dx, what is this? This is the gradient of the function this with respect to x, which is nothing but direction cosine of the line joining the satellite to the receiver. It is a direction cosine in the direction of x. So it is, we can write like this, x we have taken I, so x I value minus x 0 divided by rho I r. So this is what is the thing written here. I can take either way, this is the difference actually. So similarly I can write y r minus difference divided, this is the direction cosine, y I minus y 0 r. So like that. So this is what is the relation. Now this one is computed, we know it, we can compute this thing, and these are the parameters we can show like this, these are the thing. So this is from only one satellite. So similar to, so modified residual observation from the satellite I to receiver r at any time t, that is nothing but P r dash I r t minus f x 0 y 0 z 0 and del t 0, and this is equal to del x df I dx del y df I dy del z df I dz plus e I r t. So finally we got this expression. Now which is in linear, you can see now this is a linear relation. So we have done the linearization, and this is from only one satellite I. So if we get observation from n satellites, so we will get this type of linear relation from n satellites. So this is what we can, again we can write this thing in a matrix form. O I R T is equal to df I dx df I dy dy df I dz df I del dr del x del y del z del t. So we can write this thing in this way. Oh, one of the, I have missed one, del t del f I dt plus t. So I R T. So this is the expression we are getting from only one satellite. So if we take observation from n satellites, so we will get n number of this expression, and we can write this thing in a matrix form, O1, O2, like that, OM, m numbers of satellites. So and that can be written as like this, df1 dx df1 del y df1 del z df1 del t. Okay. So this is from the first satellite, and from the second satellite df2 dx df2 dy df2 dl2 dt. This is from the second satellite, and in that way m numbers of satellites we can go for and that multiplied by the unknown parameters del x, del y, del z, del t, and again error matrix 1, 2 like that m r t. So this is the matrix form of the error. So now if we write this in matrix form in a, so instead of this O like this, that is the O matrix, this is the A matrix, this is the unknown matrix X, and this is the error matrix. So this is the final linear form of GPS observables, which now we can solve this equation linear form by least square analysis. Now in this we have assumed, first to start with we have to assume some value for the receiver, and through iteration we will find out the error matrix X, and once this, that means we have to start with x0 and we will have the error, suppose del x, we will have some value, and this value has to be changed n numbers of times to make this del x to 0. So if we, this is the what is inside the, we will go on iterating this till we make this del x matrix, del x, del y, del z, all this will be 0, and the value for which this del x matrix, del x, this x matrix will be 0, that is, and for that whatever design matrix that value will be there, that is the position of the unknown location. So that is what it is done in this in GPS positioning, and that means from this through least square analysis we get the x is equal to transpose A whole inverse A transpose O. So this is the solution for this, that means this should be equal to 0 finally, and then what, for whatever value of this will be go on changing, this x0 will be go on changing, and some value, suppose x0n, similarly y0 will be y0n, z will be z0n, like this, and for whatever value that will be, this will be to 0. That is what is the position of the GPS receiver. So in that way we compute the position of GPS through iteration method. So that is what is it, the design matrix A and the observation residual matrix O are computed using the assumed initial value. As I told you, x0, y0, z0 are the assumed initial values. An iterative process is being carried out to determine the single point position. Iteratively we do go on doing so that del x, del y, del z, del t is 0. From the initial values, the modified values are obtained which subsequently been used to determine next modified value. That is what it is told. We will assume some value, we will make del x, we will get some value of del x, and then we will change this value in such a way that del x value go on decreasing. Process get iterated as values get converged, and finally making del x, del y, del z, del t is 0. That is what we have told. Thus the unknown position, that means for whatever value of this will be equal to 0, then that is the value of the receiver position. The other unknown position of the receiver and the receiver clock error at the epoch of observation can be determined. So that is what is in short about the GPS positioning mathematics. So summary of today's class: GPS positioning consists of determining the position of a point using GPS observable. All GPS positioning CA code GPS observable get processed, and generally we get an approximate location. From that approximate location, more precise location we do go for through phase observables. In finding out the position of GPS, one of the methods is the least square analysis method, which we have discussed in today's class. It is an iterative process through which we determine the point position. Since there are 4 unknowns, signals from at least 4 satellites are required to determine the unknown position of point. With this I will like to conclude today's class, and this is a question you should, and for further reading you can go through this book, and in the next class I will like to go for establishment of GPS, or how GPS baseline processing is being carried out, that will be shown mathematically. So with this I want to conclude today's class. Thank you.